Hello everyone, this is the Instron universal testing machine which we will use for tensile test today, and we will carry out the test for testing 3 different samples, 3 different materials, and how this will be done, we will go through this procedure now. These are the 3 samples that are going to be tested in this machine today. The first one here we have, it's the steel material. The second one we have is the aluminum material. The third one we have is the brass material. And let's proceed with the sample measurement first. You can see that we have put 2 marks here, which are blue colored marks, and this is used to denote the initial length of the sample. The initial length of sample for what we have now for steel is 44.98 millimeters, which is roughly around 45 millimeters. The next thing we need to check is the diameter of the sample. Here we are measuring the diameter of the sample, and the diameter of the sample should be measured at 3 different locations to make sure it is uniform. So here on the top we have the diameter as 8.98 millimeters. Now we are measuring diameter near the center of the sample, which is around 8.96 millimeters. And here at the end we have the diameter of the sample as 9.01 millimeters. So what we have to do is take the average of these 3 readings to get the diameter of our sample. Next we come to the computer of our machine, and here we need to do some initial settings. So first we will go into the sample parameters, which is this icon. Here we have to define the sample properties as what we have with us. So here first I will define, this is tensile steel. I will write this name like this, and here we need to select if it is circular, rectangular. For us it is circular geometry of our sample. Next setting we will do and decide is the specimen size. This is what we just measured, which was roughly around 9 millimeters, so I will keep it 9. The length of our sample, initial length, was 45, so I will enter here 45 as the length of our sample. The next setting we have to define is the testing controls. The test controls, we will just set the speed of our test, which is 5 millimeters per minute. It can be set to another speed as required in the experiment, but for this experiment we will keep it 5 millimeters per minute. Okay, now we are ready for starting the test, but before starting we need to mount our sample. So the sample needs to be mounted to our machine in the mounting area, which is here, which we will decide and show you now. Here is the lower grip where we grip the sample using this hydraulic system. So this button, you will push it, and this grips will grip the sample between them tightly, and the same way there is a top gripping mechanism. So now we will mount the sample from the circular area in the sample here, and then we will pull this button, and the sample will be gripped in our machine from bottom. You can see that. In the same way we will pull the button on the top and grip the sample from the top. Okay, good. Now we have our sample ready and gripped inside the machine, and it is ready to be pulled to make it tensile test. Okay, now we will proceed with the tensile test after looking certain parameters in the computer. The next thing we have to do is, because we adjusted the machine up and down for putting the sample in the machine, what we have to do is click on balance load, which will balance out all the load and make it 0. And again we have to do the reset gauge length. Now the sample is reset to gauge length of 0. You can see it's very sensitive, that's why the value is moving. That's okay, we have this degree of error in our system. Now one thing to explain here is that this machine, the next thing we have to do is click on start button, but before that I will explain to you what will happen. What will happen is that the machine will start pulling on the sample, and the sample will we will have an experience of load here, along with extension. So we have load on the y-axis and extension on the x-axis. As the sample is pulled together, the load starts to increase, and we will see the material behavior in the test. So let us start the test and see the sample, how the sample is pulled together and what is happening to the curve. Now the sample is being pulled, and we can see there is not much difference right now, but let me show you at the computer what's happening. You can see in the computer the load has started to increase 15 kilonewtons, and the sample is pulled by 2 millimeters. Pulled by 2 millimeters. Here we have the extension as well as load. You can see the load is increasing for this sample, which means the sample is resisting the tension which is in the in this steel sample. And now it's good to experience and see how the sample is behaving in the extension, and after some time you will see that the material is starting to reduce its thickness from the center, which is called necking. Okay, we will keep the video on and keep on seeing how the material is behaving. This is still being pulled together. You need to be very careful wearing all the appropriate personal protective equipment, safety glasses, gloves, as there can be any breakages of small parts which can cause any problem. So we are still pulling the material. You can see it's getting thinner in the center. And finally it will break. Okay, the sample is broken, and we will stop the test now by pushing the stop button here. We can see here that this is the graph we have attained for our test. The load started from 0 until 25, and then after 25 the sample started behaving plastically, and then we have this energy absorption until the sample breaks. So the sample breaking is happening at this point, and after the sample breaks we have reduction in the load. Now we will get this data from the computer by Excel and study it more for the material properties like Young's modulus, ultimate tensile stress, fracture stress, and everything, all the properties related to this material. We have to unmount the broken sample and measure its final length as well as final diameter. Here we are joining the broken sample pieces together, and after joining we will measure the final length from the same two original points, which will give us how much the sample has increased in the length, as well as we will measure the neck diameter, how much the sample reduction in the area. We can see here that our final length of our sample is around 52.27 millimeters, which is the length which is increased, which is the increased and final length of this sample. Here we are measuring the neck diameter. You can see it is very closely put to the reduction area, and here we can see the final diameter is 5.22 millimeters. Using this initial and final diameter as well as initial and final length, we can calculate many properties of this steel material. Coming back to the computer, we can add the same final readings in the sample properties here again. So we will open sample properties. In this test we can put the final length, which was 5.22. here the diameter was 5.22, the final one, as well as the final length was around 54.28 millimeters. So we have given the final specimen dimensions as well as initial. We will go now to File and click on Data and click on End and Save. In the tensile test, now we will look at how aluminum sample will behave. First, we will measure the initial length of our aluminum sample, which is 45 millimeters. Also, we will measure its diameter, which is around 9 millimeters from different locations: 9.06, 9.04, 9.09 or 8. So let's assume it around averagely 9 millimeters. We will put the sample details here in our computer for the Instron machine. This now is aluminum sample, so I will write here AL, which stands for aluminum, and here we have to give sample specifications. So it is 9.01 or around averagely this number, and then the length is set to 45 millimeters. After setting the sample details, we can go and mount the sample, but before that we can also define the test parameters, which is here. The speed is 5 millimeter per minute, which is the same as we did in the steel test. And after doing that, we are ready to mount the aluminum sample in our machine. In our Instron machine, we will move and now mount the sample in the lower grip area here using the grippers here, and then we will bring down the machine using manual controller. This is the manual controller for the machine, which is used to make the machine up and down. So once the sample is in good location, we will put the grip on the top part also. Now our sample is nicely secured in the grippers and we are ready to start the test. Here we will click the Start Test button, and then once we start the test, before starting we need to reset the balance as well as reset gauge length. Once we have started, you can see the graph is beginning to plot here, which means the force is increasing and the load is increasing. Let's see the sample behavior. Now here we have aluminum sample which is being pulled in the tensile testing machine. Now we can see the behavior of aluminum in this case. For aluminum, the difference between aluminum and steel is that there is not very significant transition between elastic and plastic region. That's why the point of yield, the start of plastic behavior and yield stress point is not very clearly defined. That's the difference between aluminum and steel. But here we will see and experience the necking behavior also, the same as steel, and we will see the reduction in area from the center. We can also look at the graph behavior meanwhile the sample is being pulled in the tensile machine. Here you can see as the load is now the load increase is a little bit stabilized, while we have this stable absorption of energy in the sample. We can also see here that there is no defined path from where the sample turned to plastic region, not sharp transition between elastic and plastic region. It is a smooth curve, which is the characteristic of this aluminum material. Let's look at the sample as it's about to break. Here we can experience already there is very slight reduction in the area from the center, but it will be more visible over time as we proceed with the tensile test. This is the point in the graph where the load is now gradually decreasing, which means the sample is about to neck from the top. Now the test is finished. Now in this case the breaking of the sample is from the top. We can see it here. This can happen during the test. Ideally we want it in the center, but sometimes it can happen from the top. Now we will unmount the sample pieces. And now we will go and measure the broken pieces of sample and see the final diameter as well as final length. Before measuring the sample, let me show you how the curve look like. It is like this, and we will get the data for this as well. Here we have put the pieces final pieces of final sample here of aluminum, and we can see the final length is 52.58 millimeters. Also we can notice that the final diameter is now being measured for the aluminum sample, where the final diameter is showing to be 5.24 millimeter, which is the reduction in the diameter. We will come back to our sample parameters in our tensile testing software, and here we will put our final diameter 5.24 millimeters as well as the final length, which was 52.28 millimeters. Okay, and click next. Okay, finish. Yes, and lastly we will end our test and save the results and get the data in Excel for further studies. Thank you. In the same way as we did the steel and aluminum sample, we have now mounted the brass sample. You can see the brass material is gold in color. Here the brass sample is mounted in the Instron testing machine, and we are ready to run the sample. But before, let's define the sample parameters. Here the sample parameters, we are doing the tensile test of brass material, and now the specimen has an initial diameter of 9.04 millimeter, which was measured using vernier caliper, and the length of the sample was the same as 45 millimeters. Let's now begin the test. Before beginning, we will test the control parameters to be the same, which is 5 millimeter per minute. And now we are going to reset before starting. We are going to reset the balance load to be 0 as well as gauge length to be 0. And now we are ready to start the test, which is by this yellow play button. Start the test. And now the sample is being pulled in the tensile testing machine, and you can see the graph is automatically being plotted here. The load is increasing, and this is the elastic behavior curve. Let's see the sample behavior right now. We can see the sample is started to being pulled, but not very visible right now as the reduction in the area is less and we are still in elastic behavior. Let's look at the graph. The graph is already still in the elastic region, you can see here, but we will see a very good transition between here from elastic to plastic region. Now we can see the material is shifting, beginning to shift to plastic region, but it's again not very defined and sharp like the case of steel. So now here the graph curve is moved from elastic region to plastic region already, but here we will use the 0.2% rule in order to get the point of the elastic stress, the tensile stress. Okay, now let's look at the sample behavior at the same time. Now the sample is still being pulled in the machine, and we are not beginning to notice any changes right now, but again the load is still increasing and the sample is still being pulled in the machine slowly and slowly. It is important to keep the video in the same view, as brass is a brittle material, and here the breaking can happen all of a sudden, and we will not notice very big area reduction, which means the necking will not happen that visible from the center of the material. So it will break without giving any clear and visible indications, as we can see now. So now it can break any minute. Now the sample is at his highest point, highest load, ultimate tensile load. And we can see now the sample break from the top area here, but again there is not clear indication of necking. You can see there is very less reduction in area, as we can see from the broken sample. Now we will unmount the sample from our machine to make the final measurements, which is the diameter. Okay, now we will measure the final length of our sample and see how much the length has increased in the tensile test. We can see now the final length is 51.04 millimeters. The final diameter of the neck area for this one is measured to be, for the brass sample, is measured to be 8.01 millimeters. Let's input this data in our installed machine computer. Here now we will update the sample details to be what we measured for our final sample, which is 8.1 final diameter, 8.01 millimeter, and the final length to be 51.25 millimeter. Okay, and now we are ready to end this test and save our results in the form of a graph. You can see the graph, end and save. Click on end and save this result, and we will save this data. It is interesting to look at our final shape of the samples and have a close look of how the failure happened, how the tensile test failure happened. Here we can see this steel sample has a cup like a shape, and there is a noticeable necking happening in the steel sample, and whereas also the grain of this material is visible at this point. This is the steel sample. Also the aluminum sample, which was here, has shown some good necking, and there is a cup like structure happening in the failure region. You can see it carefully. While when we look at the brass sample, you can see the necking is very less, as well as it is flat. Almost the failure area is flat in shape. Then that's the difference between the three samples and their failure behavior. Now it is up to you to study the curves, the Excel file we received, which is the data of tensile test for the three samples which we did today: steel, aluminum and brass. Thank you.